Okay, back to it. Example 3. We now have two blocks that are separated by a compressed spring. That's shown in green here. There's a cord that connects the two masses. One mass is m kilograms, the other is 3m kilograms. The cord keeps the spring from separating them until the cord is cut. Once the cord is cut, the compressed spring goes back to its original rest length, and in doing so pushes the 3m mass to the right and the m mass to the left. We're told that the 3m mass has a velocity of 2 meters per second. We're asked to find the velocity of a block with mass m and the energy stored in the spring. So, conservation momentum. So, before equals after. Right, before the string is cut, this is the sum of them after the string is cut. That's the momentum of the system. And those have to be equal. All right, so we also know that before the string is cut, the system is stationary. So that means P1 must equal P2 equaling 0, because both their velocities are 0. That means this whole side is 0. So 0 equals P1 prime plus P2 prime. The sum of the momentums, the string is cut, have to equal 0. Okay, so let's substitute some of our known values in here. So 0 must equal 3m, that's the mass of the block that we know about, times the of the block that we know about, 2 plus P2 prime. So when you do that out, you get P2 prime has to have a momentum of minus 6m kilograms meters per second. Remember, this m is a mass designation. It's a constant. Okay, so now to find that velocity, we know that P2 prime is just m times V2 prime. Right, so V2 prime is going to equal minus 6m divided by m, just dividing through both sides here by m, and substituting in the minus 6m here, minus second. Okay, that's our value of velocity there. Okay, now part B, the kinetic energies. Okay, or not the kinetic energies. What's the energy stored in the spring? All right, but we're going to start with kinetic energy, and you'll see why in a minute. So, let's do the sum of the kinetic energy of the system is going to be 1/2 mass of 1 V1 plus 1/2 M2 V2 squared. All right, so this is plugging in our numbers from up here, 1/2 times 0.3. And we're given that the mass, that the variable m equals 0.35 kilograms. Okay, so that's where this came from. Times minus 6 squared. The second one is 3 times 0.35 times 2 squared. And when you do that out, you get 8.4 joules. Now, there's no external forces acting on this. It's just a spring. So, the total mechanical energy is potential plus kinetic, and the energy in the beginning must equal the energy at the end, because this is a conservative system. All right, so before the string is cut, the energy of the system, we're going to call 1, is the potential energy in the spring plus the kinetic energy. But that's 0 because this thing's not moving. All right, it's at rest. After E2 is the potential energy after plus the kinetic energy after. All right, but the potential energy goes to 0 because the spring goes to its rest length. So it no longer has any energy stored in it. And the kinetic energy, the total mechanical energy of the system is just the kinetic energy. Right? So now, remember, the total mechanical energy before has to equal the total mechanical energy after. So the potential energy, from here of the spring must equal, before the cord is cut, must equal the kinetic energy of the spring after it's cut. So that means the energy stored in a spring before it's cut is 8.4 joules.